So before I start, a word not from our sponsors, but from our group. Uh, is there's going to be two little more technical talks on this, which will actually look into detail in the classic papers. And so, Anurag is this audience. Anurag, you can just raise your hand in case people don't know this. I'm sure others will. On Friday, we're going to do part one, which is going to look at the scenario up to Hopfield. And then on Tuesday, we're going to give the second talk. We're going to look at Hinton's work and try to bring it up to the present. All right. Since Anurag is going to give all the technical details, I can read all the questions which I won't be able to get to you. But I request, if you have any questions or something to talk to me, please feel free to stop me. This is a really informal kind of talk. You know, I know, so just stop me right then and you can ask the question. If it's too technical, I will probably say that I pick it up. But if it's like an immediate question you have, some clarification, please feel free to ask. First a bit about what I will cover and what I want. So this is something I found from Fabio Vesquez's towardsdatascience.com site, which I've slightly adapted. So this is what he calls the road to deep learning. So he has a few other points here which I kind of removed because to basically highlight on the ones which I thought were the key milestones on the road to deep learning. So what will I be focusing on? So as you can see, it goes from 1943 to something like 2017. Now, fortunately for me, if I just focus on the physics, I could kind of draw a line right here and say this part of the physics is really relevant. So essentially, I'll be zooming into this part. And I'll also talk a bit about the prehistory. Here, Vasquez's image just starts with McAuliffe pits, but I will show that actually there's kind of a history even behind that. And I will touch upon briefly on Turing, briefly on Rosenblatt, and how that first neural network revolution died because of an attack by Marvin Minsky and Sima Piepert. And then the second revolution started somewhere around early 80s. And Hopfield and Hinton and Sainowski were the key figures in its revival. So I will kind of just stop at towards the end of this, so to say, second revolution. And the third revolution actually started with the restricted Boltzmann machine and so on. So this is something I just briefly mentioned, but I think Anurag is going to talk about that in his Tuesday talk. So I'll leave Anurag to tackle. And the reason for focusing on this is that this part is actually has a very solid physics background. Whereas the physics underlying the more recent developments starting from 2006 onwards, they're still up in the air. I mean, there's of course very interesting physics problems there, but people still haven't figured out what's the correct tool to handle those problems. Okay, so before I get into the prehistory, how many people here have watched? Wait a minute, come to that in a moment. So this dream that you could make machines which could think or which could simulate living machines, of course, goes back a long time. So back in the 17th century, René Descartes, founder of coordinate geometry and also a great philosopher, who also was the tutor of Queen Christina of Sweden, one of the most unorthodox characters of history. When Queen Christina was in self-imposed exile in Rome, Descartes was teaching her, elements of mathematics, natural philosophy, and so on. So it is said that Queen Christina once asked Descartes, "What could you say of the human body?" And Descartes said that one would regard the human body as a machine. So the Queen apparently pointed to a clock and said, "See to it that it produces an offspring." Leaving, of course, Descartes in a kind of a tizzy. But the dream of producing machines has a kind of a pretty technological angle to it also. So how many people have watched Hugo? Yeah. Okay, quite a few. So most of you might have seen this clip already, but for the benefit of those who haven't, let me just play this. It's from somewhere towards the end of this movie, where Hugo discovers the key with which to wind up that object that you see over there. It's essentially a clockwork machine. This is what the mechanics of the 18th century used to mean by automata. I think for some reason the sound is probably off. But you can pretty much see it even without the sound. So Hugo is going to take that key and he's going to wind up the automaton. And you'll notice that it will then have a lot of wiring of gears, pulleys, levers, and so on. And then eventually it will start scribbling with its pen. Yeah, so lots of machinery, wiring, and so on. And then its hand is activated. It takes the pen, dips it in the ink well, and then starts making scribbles in the paper. So for those of you who have watched the movie, you know that it's going to produce a drawing, which is basically a scene from the famous movie by Cecil, not Cecil, but forgotten, one of the pioneers of cinema. Okay, now this is actually not a fiction, right? So if you go to museums in various places in Europe, you will actually see such clockwork machines. So this is an actual, clockwork machine which writes a letter with its quill. This is a machine which can play a musical instrument. And there was this very famous chess playing automaton called the Turk by Ulrich von Kemble. And these were all done with what we would consider extremely primitive technology, just clockwork. In fact, some of these clockwork machinery is so intricate that when they come in pieces to museums today, it's very hard for people to actually reconstruct it back, because most of the there's not much information on how the clockwork makers who did this actually managed to do it. These were their trade secret. So there's nothing written about how they worked, and it's a major hassle to actually reconstruct them if they get damaged for some reason. And of course, this eventually gave rise to the punch cards, use of punch cards in power looms by Jacquard, which of course prefigures the use of punch cards in computers and so on. But in 19th century, we had another development also where George Bull, an English mathematician, he wrote this book called Investigation of the Laws of Thought. So now, of course, Boolean logic is mostly thought of as, or mostly taught in the context of digital circuits and so on. But if you look at what Bull himself wrote in his preface, he's saying that the reason why he came up with Boolean algebra, or this algebra of symbolic forms, is he wanted to investigate the fundamental laws of those operations of the mind by which reason is performed. In other words, he was trying to automate reason. Are there prescribed rules by following which, mindlessly following which, you come with logical deductions? And he ends it by saying that this will give us some sense of the nature and constitution of the mind. So essentially, you can see the the central question of how to build intelligence right there in Bull's work. And of course, this dream of having automated reasoning continued. So in 1937, Claude Shannon, who was just 21 when he wrote his master's thesis at MIT, demonstrated that you could apply Boolean algebra in electrical circuits to resolve any logical numerical relationship. And this is, of course, what led to design of digital circuits and digital clocks. It led to another strand. So in around 1910, Bertrand Russell, in collaboration with the mathematician Whitehead, started producing this series of books called Principia Mathematica, in which they had a very ambitious goal to derive all of mathematics, starting from a finite set of axioms, just using logical operations. So they said if mathematics is complete and consistent, it should be possible to derive all of mathematics from a set of axioms using just logical operations. Of course, we know that what happened to that operation. Eventually, Gödel happened, and then Turing happened, and they showed that mathematics cannot be both consistent and complete. Turing, of course, has a role in this story also as one who kind of asked the question that suppose you claim that a machine can think, how will you test it? Or how will you say that, okay, finally the machine we have produced thinking machine, a machine which has intelligent as humans. Now, usually, like philosophers, when they start to grapple with this question, they kind of get down into this very hard to answer question of what is thinking, what is intelligence, and so on. Turing stayed clear of that. He took a very operational approach to it, and he said intelligence is what intelligence does. And so, in his famous paper published in The Mind in 1950, he proposed what he called the imitation game. So, the imitation game, he first used an analogy. He said that suppose behind the door is either a man or a woman. Now, you're going to interrogate this other person behind the room, let's say by written questions and answers, so that the voice doesn't give away the person. And you're going to try to find out whether it's a man or a woman. So you're going to try all kinds of questions, and of course, that person on the other side of the partition is trying to fool you. So going to deliberately use some answers, which is supposed to make you think that this person is of some gender which he or she is not. And so the question is, can you nevertheless figure out after some time, when you have related this person enough, whether it's a man or a woman? Then he turned it around. He said that what if it's a human being and a computer? And you are just interrogating them through some teletype, so that you don't actually see what's on the other side of the partition. So you can ask any question you like. And you're basically trying to figure out whether it's a machine which is just going according to some algorithm, or it's a human. And this is in some sense an incredible test because it completely cuts out this whole idea of how do you define thinking, where is actually is it are you supposed to have consciousness, what is consciousness, and so on. You just say if something manages to fool you, for no matter what question you ask, it's as intelligent as humans for all practical purposes. But this symbolic approach to AI is what dominated this entire period from 1969 to about 1980, where computer scientists who were working on this said that, look, it really doesn't matter what the hardware of the brain does, as long as symbolically it can manipulate and do logical reasoning, which will make it emulate human thinking. So basically, it will pass the Turing test. Now, it's a coincidence, or probably not, that around the same time that quantum physicists like Niels Bohr and Erwin Schrödinger were grappling with the question of what is life, and were coming to the conclusion that life is as much about information as about matter, you had Warren McCulloch and Walter Pitts grappling with the same question about the mind. That can you actually think about the operations which go on in the mind as essentially framed in terms of certain laws about information? So McCulloch was essentially what we would call today a cognitive psychologist, or a philosopher, and Walter Pitts was a mathematical prodigy who grew up in the streets of, I think, Chicago, if I'm not too mistaken. And he learned mathematics by essentially hiding in the library as a shelter from getting beaten up by the boys. I mean, he basically used to live on the road. And so being in the library, he started looking at his books and he essentially taught himself so much maths that when he was still a teenager and he contacted Warren McCullough immediately after having a chat with him offered him a fellowship. So between the two of them, they started asking the question that can you come up with a very simple description of the neuron so that we can start asking the question, how does the brain actually compute? And this is essentially their highly simplified model of a neuron. So if you look at a biological neuron, it looks something like this. So there would be, I mean, of course, there's a huge variation in the morphology of neurons. But if you go by what your high school textbook would say a neuron is, you would say that there's a cell body or a soma. Then there are dendrites. So these dendrites are basically giving the incoming signal. So other neurons would connect to these dendrites. And if there's activation of these other neurons, that activation will be passed on to the cell body by these dendrites. So the dendrites actually act as the inputs. Then the soma essentially will pass on the output to the axons, and these axons will connect to dendrites of other neurons, and so this is the output. This was replaced by McCullough and Pitts in this paper that they published in 1943 by this very simple operator. So they said that, look, if you consider all the other neurons which are connected to this particular neuron as essentially corresponding to inputs I1, I2 up to IN, then each of these connections are feeding with certain strengths. So let's call them connection weights. So the connection weight for the input I1 is W1, for 2 it's W2, and so on. So what you're doing is you're doing a weighted sum of these inputs. So essentially you're doing a summation Wi, II. And then this sum is being compared against the threshold. If it exceeds the threshold, then this particular neuron is activated. So it switches to, let's say, on state. If it is below the threshold, it remains inactive. So it goes to off state. So effectively, you are seeing the neuron as just an on-off switch. The only difference with the simple on-off switch is that instead of someone going and pressing it, here the other neurons, the other on-off switches, are basically switching this on or off based upon their state. So all you need is then essentially, something like this on-off devices, and then connect them into a network. So when they're on or when they're active, you say that some proposition is true, and when they're off, you say the proposition is false. And so they said that, so therefore you can do logical operations by taking the signals to be propositions, the neurons to be something like a logic gate, and the varying threshold could be used to make different logic gates. So for example, in order to make an AND gate, they showed that if you take these two inputs, X and Y, and connect them with connection strength +1, and you have a threshold of -2, then this particular neuron, which is receiving these two inputs, is going to function as an AND gate. So McCullough gave a very nice pictorial demonstration of this. So he said that, look, you can think of it like this, that the output, that is the neuron that you're looking at, is like a block G. And the two inputs, X and Y, correspond to like blocks E and F. So if only E block falls, G will not fall simply because it's blocked by F. If only F falls, G will not fall because it's blocked by E. But if both E and F fall, G will also fall. So both of these propositions need to be true for the output to be true. Similarly, he could make OR gate, NOT gate, and so on. And so therefore, in principle, McCullough and Pitts show that you can construct any arbitrary logical circuit you want with such on-off switches. And so therefore, they concluded that it should be possible to create arbitrary logical circuits using this neural network paradigm. So that's all right. That's all very well. But the problem is this. In order to create an AND gate or an OR gate or a NOT gate, McCullough and Pitts had to think really hard. So suppose you want to construct an arbitrary logic circuit for implementing a particular operation. How do you come up with the logic circuit? We have McCullough and Pitts thinking about it for maybe a year before they come up with a circuit. That's effectively same like those clockwork makers producing this toys which can only do one thing. So you want a general purpose machine. In other words, something which give a method by which you can learn what kind of circuitry is required to solve a particular problem. So in other words, you want to create a machine which can learn. And this is the problem that Frank Rosenblatt, engineer who died actually quite young, in the late 1950s, he built a machine which he called the perceptron, basically, using the word perception. This, in a sense, is the first neural network, you might say. So what he did was he took the hardware of the McCulloch-Pitts network and he came up with, well, actually not he, but it was another pair of scientists who came up with this, but he actually combined this, where he said that you can have a learning algorithm which can adjust this link weights to solve a particular problems. In particular, he looked at a classifier for patterns. So his idea is like, you give this machine various patterns. So for example, here you see an X. So this X is made out of lights which are blinking red against a black background. So if this light impinges on this board of sensors, then essentially it would be computed by a whole series of these on-off switches. And at the end of the day, there will be an output signal where you have one output block, which basically stands for X, one output block stands for A, one output block standing for O, and so on. So you'll have the output block which stands for X will light up, and all the others will remain off. So what he's doing is essentially this. You look at the feature space. So this feature could be, for example, are there two bars which are basically crossing each other? Are there three bars with a sidebar which is going vertically, or is it like a single curve? So these are the various features. And in this abstract feature space, he's creating decision boundaries such that all figures which look like X will essentially fall on this side of the boundary, and all features which look like non-X will fall on this side of the boundary. So he's basically dividing this higher dimensional feature space into two parts. And similarly for A, similarly for O, and so on. So if you take the single layer perceptron, this is basically just a McCulloch-Pitts neuron, as you can see. So the output is given by a function, a nonlinear function of the weighted sum of the inputs. And so for example, if you take this particular circuit, okay, so you have connection weight 1, and a threshold of 1.5, you actually create a AND logic. So if you look at the input space, so Xi1 and Xi2 are the two inputs. So in this space, basically this particular machine will create a decision boundary such that it will be off if your inputs are falling in this space. It will be on if your inputs are falling in this space. So if both the inputs are 1, then it will be switched on. But if the inputs are 0 or 1, 1 or 0, or 0 or 0, 0 and 0, then it will be switched on. And what he's doing using his learning rule is he's actually working out these weights. So the scheme was that you have basically your output function is given like this. So for each input pattern, you check if each of the output units is giving the desired output. If yes, then you already solved the problem. You don't do anything. If not, then you correct these weights by a quantity which is proportional to the product of the input and the desired output. So basically, you make some small changes. You are basically learning from your errors. It's like having a teacher, and every time the student is making a mistake, the teacher is like, starting with the knuckles and saying, it's like supposed to take like this much, or this is the correct answer. So this by how much you got it. So you keep doing this. Eventually, the idea is the student will start getting it right. And so this perceptron learning rule, in a sense, was the first learning algorithm which allowed you to create a machine which would learn general purpose algorithms. But the problem that this had was that it could not implement certain very basic gates like XOR logic. So XOR logic says that if both the inputs are on, or if both the inputs are off, then do nothing. If any one of the inputs is on but the other is off, then become active. So it's the space looks something like this, right? So here it should be off, here it should be off, and here it should be on. Okay. Now you see, the problem is you can't take a single line and divide up the space such that all the red points would be in one domain, or the blue point will be one domain. Any single line that you put would always have some red points on this side and some red points on the other side. So in order to correctly classify this, you need to have at least two decision boundaries. Unfortunately, with just an input layer and output layer, there's no way you can create multiple decision boundaries. For that, we need to create an additional layer. So the XOR problem can be solved if you actually introduce a intermediate layer, what is sometimes called the hidden layer, hidden because it's neither the input nor the output. So in some sense, it's invisible to the external world because it's neither the neurons where sensory stimuli engage, nor is it the neuron which directly activates the muscles, right? So once you have intermediate layer, it's very easy to see. So I've actually given you the kind of connections you need to produce precisely this XOR logic or the NAND logic and so on. But the problem is, how do you train this network? Because unlike the perceptron, where you could use the product of the input and the desired output as the correcting factor, here, for the hidden node, you have no way of accessing it. So how are you going to know that the connection weights are correct? So for a long time, after Minsky and Peppert pointed this out in their book Perceptrons, so this came out in 1969, effectively all work on neural networks stopped. So it was very unfashionable until in the 1980s, there were people who independently discovered an algorithm called the backpropagation algorithm, which could actually train networks with arbitrary number of layers. All right, and that eventually, and this is something, I'm going way ahead of the story, from 2000 onwards, you basically started having, improved algorithms which could actually train networks with arbitrary number of intermediate layers. And when people started looking at what kind of representation were these intermediate layered nodes supporting, they found that this input layer were recognizing things like, simple geometric patterns like edges oriented at various angles. The first hidden layer was recognizing things like contours, like circles, curves of various kinds, or edges, like, this L-shaped. And then the second hidden layer was basically, building these components into, some kind of triangles or eyes or whatever. And the output layer was finally putting them all together to create various kinds of faces. So one of the biggest surprises is that it turned out that this is precisely how our visual cortex also works. Yeah.
How they tackle this problem of dividing the weight?
Yeah. So what they did was they said, all right, we will give some input, we will have arbitrary weights, go and check the output. Most of the time, the output will be completely wrong. So what we will do is, we will first figure out what are the weights needed for the last hidden layer to the output layer. So you keep changing it until you start getting the correct answer. Then you try, okay, what will be the correct weights between the last hidden layer and the second but last hidden layer? And then the second but last hidden layer and the third but last hidden layer until you come all the way to the first hidden layer and the input layer. So that's why it's called back propagation. You're going back.
Change the last but one layer. Yeah. Okay. You will not have to go to the last layer.
Very good. So you have to do it accurately. So once you do this whole cycle, you have to repeat the cycle again until you get it right. So one of the big questions for the earliest neural multiple perceptrons was, will it converge? So this convergence was one big question which people showed that if you have very fast rates of learning, it will tend to overcorrect and it will not converge. So you can't have a very high fast learning rate also. So there are optimal rates at which you can learn and so on. So you have an error, right? So that error you are using to modify the first, the output layer to the first last hidden layer rate, and then you use the last hidden layer's output to correct the last and last but one hidden layer, and so on. So you back propagate. But then you go back to the input to the first hidden layer. Then you run the whole procedure once again. So you give the input, you see what's the output. Again, you see that it's making a mistake. So again, you do the procedure all over again. So you use a set of what is called the training set. You have pairs of input and correct output, and you use that to basically keep changing the weights until for the entire training set, it's giving you the correct result. And then hopefully your network is ready and you try the test data set. Okay, so it turns out that the primary visual cortex is somewhat built like this. So if you look, and this was actually found out by Hubel and Wiesel, for which they got the 1981 Nobel Prize in Physiology. So they found that if you look at the primary visual cortex, which is like the first region of the brain which receives visual stimuli, for a long time they were studying cats and they were planting electrodes. I'm told this is a very human experiment. No cats were harmed during this experiment. The idea was you show it various visual stimuli, and when this neuron that they're recording from starts firing like mad, then you know this is what is it. And for a long time, they try out various visual. So they had all those transparency slides. Not sure how many people have actually seen that one. They doesn't do now. So basically, they had a transparency projector. They would put these plastic sheets with various things drawn on them, and then it will project it on the screen, and the cat's head is fixed so that it can only look at that place, and then it's recorded from there. Now, whatever they tried, nothing. So suddenly, once while changing one slide, during the time they were like, they are like have one slide out, suddenly it starts chattering like mad. And then they put the slide fully in, nothing. And then after a few trials and errors, they realized it's not responding to what's on the slide. It's responding to the fact that the slide, when we move, casts a shadow of a particular angle on the wall. So if they see a shadow, which is a vertical bar oriented at a particular angle, the neuron is responding to that. And so then, experimenting with different neurons, they realized that these neurons in this P1, the primary visual cortex, actually respond to bars, dark bar against a light background or bright bars against a dark background, which are oriented very same. So each neuron is specialized for a particular angle of orientation. So then they were very puzzled. Okay, so then that means they are kind of only responding to edges. So how are they actually making sense of a full object? So then they realized that the next layer of the brain is basically responding to like combinations of these edges. So you take two edges and you join it at various angles. So each of these neurons will respond to these various things. And so on. And so next highest layer will take combinations of these edges, these corners and so on. And this actually,
I didn't understand that. How do they identify? I mean, they wouldn't know which one is the next layer. Right?
No, anatomically you know, because you know which connection, where the V1 connections are going to. So that they can do. No, but this actually gave rise to a major conundrum. So they said that this is how you form a percept of a, let's say, a face. So when I see your face, I recognize it as a protein. What I'm doing is, my first visual layer is actually breaking your entire piece into the edges of various angles. My second layer is going to join up all these angles to, let's say, identify various places where you have sharp corners. The third layer is, let's say, recognizing your nose, your earlobe, and things like that. So by this logic, that means deeper and deeper as we go into the brain, it must be recognizing more and more specific. So I think it was one Mountcastle or some neuroscientist like that, who said logical extension of this will suggest that deep inside your brain, there is a neuron which is specific to the piece of your grandmother. which will fire only if your grandmother comes in with you and no other time. Because it actually combines all those specific features with a specific hero grandmother. So this is the so-called grandmother cell hypothesis. Now, it also means that if something happens to that neuron, you're never going to replace it. So for a long time, people use this grandmother cell hypothesis to argue, oh, it can't be true. You must be using some other, they must be using some other method of recognizing people. It can't be like the specific neuron you say. Until, of course, like about 15 years back, a few neuroscientists who were working with, I think, patients undergoing brain surgery. And before the surgery, they were trying out like, some research experiments. And they discovered the Jennifer Aniston neuron. So apparently, there was a neuron in this patient's brain which would only respond to pictures of Jennifer Aniston and to nothing else. You show it Angelina Jolie, nothing. You show it Eiffel Tower, nothing. Jennifer Aniston, good man. So, and you can show Jennifer Aniston in various orientations. You could show Jennifer Aniston's publicity skill. You could show Jennifer Aniston in Friends or in one of her movies. It will happen. But you show like anything else. You show Brad Pitt with Jennifer Aniston. Right? So, I mean, it only is you kind of uniquely responding to Jennifer Aniston. Now, there's still a lot of debate as to how to interpret this, but it just shows that, when we poo-poo an idea saying, oh, it can't be, it contains nonsensical bias, is rich enough to come up with anything. So, one of the big, yeah.
Single neuron is firing not a group of neurons.
No, it is single neuron. That's the surprising part.
Is it possible it might also keep 5 or 10 copies at different parts?
Perfectly possible, but the possibility of you hoping later that random and coming up with precisely that neuron, the other neuron which recognizes Jennifer Aniston is pretty low. I mean, I'm still puzzled. Where did they get this idea of showing pictures of Jennifer Aniston?
Also, previous question. It is a single neuron, but it gets its inputs from a neuron.
Of course.
Yeah.
So it is getting inputs from many different layers. So that's how it's combined.
So we can view it as maybe an output there for the reference.
Correct. But it also seems that there is a neuron which is specific to Jennifer Aniston, which is mind-boggling.
So, is it know how many layers the brain has?
Well, there are anatomical layers. So you can, for example, the thing is that your brain is too complex to actually fully map it out. So parts of the brain has been mapped out. The visual cortex in particular has been mapped out in quite great detail. And anatomically, we know that there are, I would guess, about something like 10 layers. But see, we are not just talking about visual. We are also talking about parallel streams of auditory, olfactory, and there will be other, non-sensory kind of processing things going on. So it's very hard to say exactly how many layers is going on.
But the number of things that we can categorize and classify to some I don't know. Wouldn't the number of neurons be insufficient in the brain?
That is precisely why people didn't believe the grandmother cell hypothesis. So we have roughly about 10 to the power 11 neurons, and clearly not all neurons are responsible for these kinds of memory recall tasks. So it seemed a bit unusual to expect that there would be dedicated neurons for remembering particular pieces. So that's why I said that this experiment is still quite controversial as to how do you interpret this. Could there be other interpretations rather than the grandmother cell? But the reason why I brought this up is that a similar issue has now challenged computer scientists who are trying to understand how these large language models work. Like, for example, what are the hidden layers actually represent? So this is a cartoon which says that, one way in which it will be working is precisely the way human brain works. So, you show a face. So first the layer breaks it into the edges. The second layer, combines into corners and contours. The third layer combines its corners and contours into various face-like image. And finally, you have the output, which basically corresponds to a certain neuron firing. Oh, it's Joe, or oh, it's Chris, or oh, it's me. But figuring out how it's generally for any given problem, what exactly are the hiddenness representing remains an open problem. And it's actually a very crucial problem because unless we understand how this large, deep neural networks are working, what's actually going on in the hidden layers, they will always remain somewhat magical blackboard kind of thing. We won't be able to know when they are going to get it spectacularly wrong. So now we'll kind of step back a bit and take another parallel strand which was going on about the same time. So going back to 1940s, in 1949, the Canadian neuropsychologist Donald Hebb wrote this book, Organization of Behavior, in which he talked about how do you learn. Okay, so the learning that Rosenberg was looking at was, in something like that, as Raoul put it, gradient descent. You just take the output, actual output, you look at the desired output, look at the difference, and then basically try to feed it back, adjust the calculation. But Hebb was interested in the rate. He wanted to know how is it that we learn and not how we would like it to learn. And he came up with this very simple-minded argument, or not simple-minded, rather simple argument. It was actually quite a bit of thought which went into this. So essentially what he said can be reduced to just saying neurons that fire together, wire together. Now, essentially what's happening is that when you have a cell which is near enough to excite another cell, and whenever cell A is excited, cell B is excited, this causes the synaptic weight of connection from A to B to gradually become stronger. Conversely, when A fires, B doesn't fire, or when A doesn't fire and B fires, this strength is going to get weaker. So if you want to have a good analogy for this, just think about how our friendships grow. So if you and another person are, always smiling at the same jokes, or you kind of are always enjoying the same things, and then when your friend is sad, you're also sad, your friendship is going to get stronger. But if you laugh at the other's misfortune, friendship won't last, So it's very much like this. So when both neurons are coactive, connection gets stronger. When they are not coactive, when one is off and the other is on, the connection gets weaker. So this simple Hebbian prescription was thought to be, just a cartoon version of how we learn, until again, experiments showed that the brain actually does that. So in 1966, the first empirical observation of this Hebb rule was done, and the biologists called it long-term potentiation. So they found that if consistently neuron A firing is followed by neuron B firing, the postsynaptic potential, that is the probability of the next neuron being activated by the presynaptic neurons firing, keeps going up. On the other hand, if the neuron, next neuron, the neuron which is actually receiving input, first fires and then the presynaptic neuron fires, so which is opposite of the causal relation, gradually the strength would be weakened. So this is in some sense nothing but Hebb. Okay, and so this gives us a clue as to how human memories work. So human memories are very different from computer memories, because how does computer memory work? Yeah.
That there's some other entity which is saying whether they should be fighting together or not.
No.
Then how do you decide whether it is the correct relationship or not?
So it's a very simple thing. It says if neuron A gives output to neuron B, so neuron A is presynaptic, neuron B is postsynaptic, then if neuron A firing is followed by neuron B firing, so they're coactive, then the synaptic strength, so the number of neurotransmitters will be emitted when neuron A fires, will be combined by neuron B fires. That keeps strengthening, or that keeps increasing. So in some sense, the connection strength gets stronger. But if you have the opposite effect, that is, this fires, but nothing happens here, or even more, this fires, and then this fires, which is violating the causal chain, then the connection strength is actually weaker. You have less neurotransmitters coming out. So this is basically a lot of biochemical reactions happening in this body. So maybe we'll take that up later because this like takes you away from the. So this is actually going to give rise to an explanation for the peculiarities of human memory. So how does a computer memory work? So the random access memory essentially you need the address. So the computer may have something stored, but without the address, you're blank. So when you wipe your hard disk, information is still there. What has been deleted is simply the mapping from the address to the data set. It's still there. So forensic, computer scientists can go into your hard drive and start retrieving the data which is so-called lost. Okay, I'm a beneficiary from this because some idiot of the computer system actually wiped my hard drive without realizing. And then yes, Mani and Ravi had to basically retrieve all the threads of the data. But they were all there, but of course there's no link. So it's almost as good as it not having it. So like you have to go and find each file and see what's in there. So in contrast, humans have the so-called associative memory. So what is an associative memory? So I call it the Proust effect because in Proust's book, Remembrance of Things Past, he portrays this very poetically. So he describes how in one day, he kind of, after a very tiring day, he goes home and he takes tea with a Madeleine cake. As soon as it goes into his mouth, he has a sense of pleasure. And when he takes a second mouthful, it calls into his mind a memory of how on Sunday mornings his aunt Leonie used to give him crumbs of Madeleine at Combray. So that a memory of something from deep in his childhood. And every one of us had this kind of flashes. Right? So we smell something and it suddenly reminds us of something which happened deep in our time. It happens to me all the time with, for example, books. So I call books to be like 10 seeds of Harry Potter because I've taken books which I, for example, first read when I was a kid, and it would immediately take me back exactly to that time in school, in that class, when I was actually reading that book. So when you take physical objects, sometimes just the holding that physical object takes you back, years back to when you first handled it. So this way of taking piece of a memory and using that to retrieve the whole memory of what happened that day and so on is what we call associative memory. In computers, this is no use. I mean, it's no use saying that, okay, that file had this thing and try saying that to this, try telling it to them. Where we're going to stare you down and pick you out of the. So, you have to be much more specific and, you have to have some systematic way of retrieving your files. So the question is, given that Proust has described this so beautifully that human memory is associative, but how do you actually construct it? How do you actually have such associative memory? And so this is where Hopfield comes in. So Hopfield, so I'll go into his model in a second, essentially proposed a model in which he showed that, look, you can explain this associative memory if memory basically behaves as a system which has multiple attractors. Attractors are essentially any state being defined by activation fields of various neurons. Any state which basically has all other neighboring states converge to it after a long time. So for example, you can start with a pattern looking like this. So you can think of it as basically certain set grid of neurons. The ones which are active are colored black, the ones which are inactive are colored white. So over time, they are gradually changing as you update the neuronal states following the McCulloch-Pitts model. Eventually, it converges to the pattern A. And similarly, you could have pattern B, pattern C, pattern D, and so on. And so essentially, any pattern which is essentially close enough to look like A, you will eventually converge to this pattern A. And so you say that from this noisy A, so this is this trying to answer the question, how is it that you have these various ways in which we write A, but we still recognize it as an A? How is it that we can generalize over a lot of variation? What is the A-ness of the letter A? So what Hopfield did in 1982 was basically take the McCulloch-Pitts framework, combine it with the Hebb learning rule, and came up with this model for associative memory. Now, so what he's doing is that he's basically having n neurons, each of which are just on-off switches. Each neuron is receiving inputs from all the rest of the neurons. So basically, it's all-to-all connected graph. And what is happening is you're just taking a weighted sum, and you're taking the sign of the weighted sum of these inputs to decide what is going to be the current state of your output. And because he was a physicist, he said that, okay, instead of just binary 0, 1, I will just use -1 + 1 so that I can think of it as basically spins. Okay. And there is no noise in his first model, so you can think of it as just deterministic dynamics. Okay, so far so good. And the problem was that there was someone else called Little who had 8 years back proposed almost the same model, McCulloch-Pitts Hebb. But Hopfield had an ace up his sleeve. He made the obviously wrong assumption biologically. He said, let's assume that the connection weights are symmetric. So in other words, if I is connected to J with weight W, J is also connected to I with J, the same weight. Now this is so patently absurd and wrong, any biologist would shudder at it. Because we know that synapses are always directed. A is connected to B, but B may not be connected to A. Even if they're connected, A to B may be excited to, so it's a plus connection, B to A may be inhibited. And even if they have the same sign, it's very, very unlikely the weights are going to be numerically the same. But this was a brilliant step backwards, as the physicist Daniel Emmett later wrote in his book, Modeling with Function. Because this allowed him to write down a Hamiltonian, an energy function. So he said that, look, if I do this, that if I find out the weights by just using the Hebb rule on the patterns I wish to store. So the patterns are simply, sequence of certain neurons active, certain neurons inactive. So you can use pictures where you say that if it's an X, then all the places where the X is located, the neurons are on. All the places where the X is not occupied, the neurons are off. So similarly, a triangle, waves, something which looks like an inverted anthropomorphic shape, and so on. So each of these I can represent as a spin array, a +1. So I can say +1, +1, -1, -1, -1, +1, +1, +1, +1, +1, -1, -1, -1. So I can write down this entire figure as basically just a spin configuration. And then I just look at the product of the ith and the jth spins for the particular pattern P, and then sum over all the product pairs to find what is the connection weight between I and J. So this is just Hebb. The moment you do this, you have a network where the attractors correspond to precisely the patterns we wish to store. The Hebb rule ensures that the energy minima are precisely corresponding to the spin configuration which you stored using the Hebb rule. So the advantage of using the Hebb rule is that now you can sculpt your energy landscape of your spin model. You can design your energy function such that its minima corresponds to the patterns, the spin configurations which you want to make this. So starting from a pattern like this, so suppose you store a pattern like this, like a dog, you mess it up very much, but then you allow it to converge and it will converge to precisely the shape of the dog. So for example, let's take this example. Suppose you just have a 3 neuron network. So you have 1, -1 and -1, -1, which are the stored patterns that you wish to store. So when you use this Hebb rule, you get this weight matrix. So if you use this weight matrix, you'll find that starting from any other, 3 spin configurations, you will flow to either -1, 1, -1 or 1, -1, 1. And this corresponds to the basin of attraction of this, and this corresponds to the basin of attraction of this. So for a single pattern, it's very easy to show that this is nothing but the Ising. So essentially what you have are 2 configurations, the one pattern you wish to store and its exact complement, the minus of that pattern. So all the ones replaced with -1 and -1 replaced with 1. So it will have a very smooth energy landscape starting from anywhere you're going to flow to, either the pattern itself or its exact complement. Problem rises when you're trying to store many patterns. Because now if you look at the input which is actually falling inside this argument of the sign function, you find that there is a term which will take you to the desired pattern, but there's also interference term because of all the other patterns which may have a -1, whereas the desired pattern had a +1. And this produces an interference or crosstalk. Now, provided this is small enough, the network can actually correct, or network can actually dominate over this, and so you can still get back the original pattern. But if this is too strong, you will actually not be able to correct the original pattern. And the reason,
Say, what is the energy function?
so the energy function is simply your classical easy Hamiltonian summation. Wij SI with a minus in.
Summation over any.
With summation.
The Hamiltonian previous peak.
You mean this one?
Yeah.
So this is over pattern. So if you wish to store only one pattern, it's easy. It's just xi a into xi j. Okay. The ith bit of the pattern you wish to store times the jth bit of the pattern you wish to store. But if you wish to store p patterns, then you basically sum over the pairs of all of them. And this is what leads to the frustration. So basically what is happening, why you get in trouble when you have many patterns, is frustration. And frustration is easily illustrated by the eternal love triangle. So you have three characters, and depending upon what kind of relations they have, you could have a very balanced configuration where you can always find a configuration which will satisfy all constraints and you have an energy minimum. Or you could have an unbalanced configuration where you can never completely satisfy all constraints, and you will have a dichotomy as to whether to have the spins configured this way or that. And of course, physicists have encountered this in random magnets, essentially spin glasses. So these are materials where you dope essentially non-magnetic material with magnetic impurities. And because of the very strange nature of the interaction, this is the famous Rudolman-Kashua-Yoshida interaction, the interactions are effectively random between this magnetic spins. And so you could have a situation like this. So this is like the case of the ferromagnet where all the interactions are positive. But if you have an interaction like this, where it's positive between these two spins and negative, negative, negative for these spins, so then what happens is suppose you make one spin go down. So to satisfy this constraint that it should be a negative interaction, you make the spin up. Then to satisfy this negative interaction, you make the spin down again. Now the question is, what will you put here? If you put an up spin, it will conflict with this because it's a ferromagnetic interaction, it should be down. But if you put a down spin, it will conflict this with this because it's an antiferromagnetic interaction, it should be up. So you can't satisfy all constraints. And so you'll have two low-lying, energy wells, neither of which are global minima, but you can toss between them. And so if you have many such spins, you will have an energy landscape which looks like this rugged energy landscape. And instead of going to the local minima, it will get instead of going to the minima which correspond to the stored pattern, you'll get stuck in one of these, fictitious memories. So you will get stuck in a non-energy minima kind of pattern. And so this is what Hopfield kind of illustrated his network as. So you have these patterns which basically correspond to something like global minimum, and basically you can get stuck in local minima if you try storing too many patterns. So I'm out of time. So yeah, I'll just very quickly flash to the side. So I don't think I need 10 minutes. So basically now you can put in temperature. So this was all in zero temperature. We just do gradient descent, just going down the energy value. But if you have temperature now, there's a small probability that you can actually go up the energy value also. And so then the question became, how do we analyze the parameter space where along one axis you're plotting how many patterns you're storing relative to the number of neurons. So this is the alpha parameter, which is the number of patterns you're storing relative to the number of neurons. And here, this is the temperature. Okay. So this corresponds to the zero temperature dynamics. So this is effectively identical to the Ising interaction, Ising ferromagnet. But the moment you have, not this one. So the moment you have alpha greater than 0, you have frustration in the system. And so therefore you have this multiple wells, and it becomes more and more hairy as alpha starts becoming larger and larger. So you go from a situation where the stored patterns are the lowest minima, but you also have a few other minima which can trap you for a while, to here you have the metastable state where the stored patterns are minima, but they're not the lowest. The lowest minima are actually some very fictitious memories. To spin glass, where actually the stored patterns are not minima at all, and you have spurious patterns which are the attractors, to finally the paramagnet at very high noise, at which the state is basically just flowing around. And this parameter space diagram was actually worked out not by Hopfield, but the physicists who got into the field as a result of Hopfield's classic paper, which showed, hey folks, neural network is nothing but spin glass in designs. So suddenly you have people like Daniel Lavie, Hannah Goldfreund, Hans Sapolsky, who basically knew the mathematical tricks of spin glass theory. And Giorgio Parisi, who won the Nobel Prize a few years back, actually also played a big role here because he gave the replica symmetry breaking technique, which became very useful. Because replica symmetry breaking is what you need if you want to solve the mean field model of spin glasses. So they started applying these tools of the trade and worked out this analytic. So that's where actually the physics comes in, because spin glass theory, so esoteric kind of exotic part of condensed matter physics, it was interesting, but by itself it wouldn't have pulled in so many physicists working on various facets of it. But the moment physicists got this connection with neural networks, they came in droves and started solving various problems. Like, for example, asking, how many patterns can you reliably store? This is a question that you couldn't have answered before. So asking like, how many patterns can you store in a neural network such that there's the very high probability starting from a nearby pattern, you will actually converge to a pattern, the actual pattern. This was answered by Ahmed Gutfreund and Sampolinsky by showing that essentially this corresponds to this maximal loading capacity, which is what we call alpha C. So this is like 0.14. In other words, if you are storing 40% n number of patterns, that's kind of the limit you can get with Hopfield. Beyond that, you will not be able to reliably converge to the stored patterns. And surprise, surprise, in 2003, people found that attractor networks are actually there in cortex. So it seemed, the lesson seems to be, no matter how outlandish, remember, Hopfield started with that horrible assumption, Wi equal to Wgi. Any biologist worth her salt would have said this is nonsense, I will not look into this point. Well, biology is crazier than what we think it is. So you have attractor networks in the neocortex which are behaving essentially like that, even though that basic symmetry is violated. So this is just to say that you can actually put in structure in the Hopfield network. So we know that brains are modular, and so what this student Neeraj Pradhan, who was basically a master student from BITS, he was working on a project with me, and much to our surprise, he found that if you look at a modular Hopfield network, actually there's some optimal modularity in which the basins of attraction of the stored patterns are the largest. So there's an optimal modularity. Below that, you get this high basin entropy, and for a homogeneous network, again, you get high basin entropy, but somehow it works best when you've got an optimal modularity. I'm just going to skip it. If anyone is interested, you can talk to me later. This is basically related to modular networks having multiple time scales. So it was converging very fast to the modular pattern and then slowly converging at the network level. And then Dennis Bray, in a paper in '95, showed that you can use the Hopfield network modeling paradigm even at the level of a single cell, where you can look at signaling networks as essentially being trained exactly like in a Hebrew, except that this occurs through evolution, whereas in the Hebrew, you are doing it through learning. Okay? So you can make the signaling network to a particular kind of response to a signal just by having evolution gradually walk through all these patterns. Okay, now the problem is, of course, the brain has also a hierarchical element. So far, Hopfield was just basically a flat plate, right? But we know from our high school biology that the brain is arranged in this way. There are sensory neurons, there are interneurons, there are motor neurons, and any stimulus first has to stimulate the sensory neuron, which is then processed by interneurons, which then goes to the motor neurons and finally leads to action. And some recent work of ours, which is done with Anand and Shakti, where we actually show these hierarchical layers where they are in the human brain and a few other organisms. So it turns out that the brain network has both modularity as well as hierarchy. And so the question is, where is the hierarchy in all these models? So that's what Hinton and Terry Sejnowski actually did in 1985. So they said that, okay, suppose we take Hopfield model, but not all the nodes are directly interacting with the sensory stimulus. There are a few hidden nodes which are just processing information, which are not directly perceptible to sensory stimulus. But in all other ways, it's exactly in the Hopfield model. Now, they found that this is way more powerful than Hopfield model because now you can introduce higher order correlations in, for example, SI, SK, which is not just trivially linked to the mean or the pairwise correlations. So this is exactly the way, for example, introducing a hidden layer made you capable of producing logic gates, which the single layered perceptron could not do. But training such Boltzmann machine turned out to be very hard. And so in 2005 or 6, Hinton came up with this idea of the restricted Boltzmann machine, where he basically turned it into a bipartite network. So he said that, okay, there are no links between the visible nodes, no link between the hidden nodes. All links are between hidden nodes and visible nodes. Okay. And this is what eventually gave rise to the first deep neural networks, where the first restricted Boltzmann machine in a sequence was trained using a given stimulus. Then the next restricted Boltzmann machine was used to train the hidden nodes of the first restricted Boltzmann machine, and so on down the chain, eventually giving rise to training down deep neural networks. Okay, so this is just basically saying that this is our group's hypothesis that the next revolution probably would be to introduce both the modularity and the hierarchy in the neural network, because the modularity in some sense allows information of different tasks to be processed in parallel, but you also require hierarchy to produce transformations. And so in practice, a modular hierarchy is the way brain seems to be doing it, and probably introducing such modular hierarchy in neural network architecture would be the way to go. Okay, so with that, I'd like to end this talk, and if you have any questions, please feel free to ask.